The next day over. If you All right, it's 5:30. Let's go and get started. All right, good afternoon, everyone. How's everyone doing today? Good to hear. So last week before spring break, so hopefully that's exciting, but that also means the project is due soon. Questions have definitely been ramping up. I am a little bit behind on my emails just because today's kind of just been a little bit of a busy day. But I do plan on getting back to you. So I know, there's quite a few of you who sent emails. I have seen them. I just haven't had a chance to respond. So I'll do that when I get back to the office after the lecture today. Okay. But the plan for this week is for us to do activity 5. So we took a little bit of a break. Just because, I thought it would be more appropriate to do the activity right before spring break. So, this is kind of all, so today's kind of the build up for activity 5. And then Thursday, we're going to do activity 5 as kind of our last thing we do before the spring break. Okay. But of course, the thing that's on everyone's mind right now is the midterm projects. Remember, midterm project is due next Friday, so the Friday of spring break. So, definitely, ask your questions. And so if you're having trouble with the meshing or the boundary conditions or, things are failing, send me an email, come talk to me, make an appointment. I'm here to help. Okay. Now, next week, I don't plan on having office hours next week during the spring break, but I will be available for questions over email. So if you have questions next week, don't be afraid to send me an email. If you want to make an appointment next week, just to kind of talk one-on-one about your project, if you think the issue's a bit too complex for an email, just let me know and we can kind of schedule a time for that as well. So, I won't be, I won't have my regularly planned office hours unless a lot of people request it for next week. But I will be available for emails and as well as appointments for whatever times I work for you. Okay. Now this week I do have one more office hours. I do have office hours on Thursday from 2:30 to 3:30. So make use of that as well. But definitely ask your questions. And if you haven't gotten to the stage where you're trying to run the simulations yet, I would definitely give it a try because these geometries, both of them, may seem simple kind of on the surface, but they each kind of have their own challenges associated with them. So they're definitely not as straightforward as our activities in terms of meshing it, applying the boundary conditions, and getting a result. So there's I think most people are seeing that there's a little bit of extra work that you have to do in terms of getting the mesh to work or the simulation to work, and so definitely don't leave it off purpose. Okay. Okay, besides that, I did grade your guys' activity fours, yesterday. So just a reminder, I only, for this class, I only grade the activities based on completion. But, I am reading your guys' reports and I do leave you guys comments, based on kind of what I read. So for this activity four, I did focus mostly on the mesh convergence test. Just because, I felt like that would be useful for the intern project coming up. So make sure you read the comments. Read the comments on activity three, although I think a lot of people kind of did, because I did see a big improvement from 3 to 4. But make sure you check out the comments I wrote for you for activity 4 before you do the project. Okay. All right. Any questions I can answer before we get started for today? Okay. All right. So let's go ahead and get started. So the topic for today and topic for this week are what I call transient finite element simulations. Okay. So transient simulations are actually a very interesting topic. And depending on the type of work and the type of analysis and the type of systems that you work with, you might work exclusively with transient FEA simulations. And so there's a lot that we can dive into here. But for this class, the way that it's kind of structured, we only have a week to kind of talk about it, which is kind of a shame. But just know that there's a lot out there. Okay. So transient FEA simulations are nothing more than just simulations of engineering systems that change with time. Which is a big kind of shift in focus and kind of what we have been doing, because everything that we've been doing so far in this class has all been static simulations. So those are situations that do not change with time. So trans is kind of the opposite. And so most commonly, you're going to find these types of situations whenever you have some kind of dynamic response. Okay, so either a load that's being applied on your structure is changing with time, or maybe you have something that's occurring on a very quick basis, and you're going to have your response change with time as well. Okay, so transient simulations and dynamic response, they kind of go hand in hand because they kind of mean the same. So, I think for the first time in this class, we're actually going to use a tool in ANSYS that is not static structural. So we're going to move away from that for the first time. So ANSYS actually has a few different tools or a few different packages to do transient simulation. And so we'll kind of mention them a bit, So the first one, the main one that we're going to use is something called explicit dynamics. And so we'll talk a bit later on kind of what that means in terms of, especially what the explicit means. Okay. And the other tool that's in ANSYS that we're not going to use, although the setup is very similar, is called transient structure. So if you want to do time-dependent or unsteady structural simulations in ANSYS, those are the two main packages that you can use. Okay. Now, any phenomenon that you can simulate with FEA, you can do in an unsteady context. So you can also do an unsteady thermal simulation. So there's a package for that. You can do unsteady fluid simulation, although most fluid simulations are going to be transient just because fluid is always in motion. But for this class, we focus mostly on structural mechanics, structural dynamics, and so we're mostly going to use these two, specifically explicit dynamics. Okay. So when we do our activity on Thursday, we're going to use this explicit dynamics. We're going to do that instead of static structure. Okay, so like I mentioned, unsteady numerical simulations in general, so not just finite elements, and so this goes for finite difference and finite volume as well, is a very, very rich topic, and it's really kind of impossible to kind of go over all of it in one day. And so kind of my goals for today is to kind of get you used to kind of some of the lingo, some of the terminology that's used in these dynamic simulations, just so you kind of know what to expect, and also a little bit of review in terms of what kind of behavior do you generally expect from a dynamic structural response as well. Okay. So today's going to be kind of like a mishmash. We're going to go a little bit fast just because there's just a lot to cover in one day. But just know that there's a lot more that we can talk about. Okay. And so traditionally, a lot of these topics are kind of taught more in kind of a numerical methods course. So I've never taught the course here, but I expect them to teach this. And so if you take the course EGGM 403, that's typically kind of what this is about. And a couple of electives that we have here too. So we have 417, which we haven't taught in a while actually, and computational fluid dynamics, which is a course that's being taught this semester by Dr. Mayoral. Those courses go more into that. But today, we're just doing one day. Right. Okay. Any questions on this so far? Okay. All right. So let's review a little bit of dynamic response first. And to kind of illustrate this, to kind of give us an analogy, let's use a mass spring damper. Okay, so let me go ahead and draw our mass spring damper here. So we have a wall, which is where our mass is going to attach to. We'll say the mass is on wheels, just so we can kind of displace to the left and right. Okay. And then attached to this mass, we have a spring. So that's going to provide our structural stiffness. Okay. So our spring has a spring constant K. And then to provide damping into the system, we have a dash pot. So the dash pot or the damper here that represents any kind of energy loss that comes, usually due to friction in the system. Okay. So usually we give that the coefficient B. And then pulling this entire structure is a horizontal force F. Okay. So if we model the behavior of the mass, and so usually for the mass spring damper system, we are interested in the motion or the position of the mass M. Okay. And so what we're modeling here is this position here. So X here represents the position of the mass M. Typically, we model this response using a second order ordinary differential equation. M multiplied by the acceleration, but acceleration is nothing more than just the second derivative of position. So that's d squared x dt squared plus c dx dt plus k times x. That is our spring term here. That's our Hooke's law. That's equal to F. Okay. where F here can be a function of time, okay? So it's not just a static force, so this is a force that, you know, we may push it, we may pull it back, push it, pull it back, that's something that we can kind of change with time, okay? So this here is our equation of motion. Or the mass position. Okay. So this is just an ordinary differential equation, but there's actually a lot of information you can kind of glean from this. And in fact, you know, a lot of the intuition that we build from the mass spring damper, you can kind of apply that to larger, more complex systems as well. Okay. And that's kind of the goal that I'm going to go with here. All right, any questions on this so far? Okay, so before kind of talking about the response, you know, let me kind of just make the comment here that most structures, or pretty much all structures, no matter how complex, you know, you're always going to have a sense of, you know, how much mass is in the system, how much stiffness is in the system, and you know, maybe you might have some sense of how much damping or how much friction is going to be within the system as well. So mass obviously is very easy to figure out. You can just compute the mass of your entire system. Stiffness is going to depend on things like the geometry and the material properties as well. So whatever you choose for the Young's modulus, that's going to affect the stiffness of your system. And the damping oftentimes is a function of you know, how the different parts of your system interact, kind of the geometry a little bit. So, you know, usually you're going to have some sense from that as well. Okay. So the goal with this mass spring damper, and kind of the reason why it's brought up, you know, probably, you know, this is probably the 13th or 14th time you might have seen this in your engineering classes. So the reason it's brought up so much is because a lot of the intuition, a lot of what we kind of understand from the mass spring damper applies to more complex systems as well. Maybe not the exact solution, but at least kind of the character of the solution and the and kind of the general behavior. Okay. So let's take a very kind of specific situation for our mass spring damper, which is going to be kind of related to what our activity is going to be on Thursday, and let's apply an impulsive loading to our system. And so an impulsive loading is nothing more than just a loading or a force that occurs over a very short period of time. Okay. And so if we apply an impulse load, so kind of the analogy for an impulse load is, you know, I like to think of it as just, you know, I call it like a hammer blow. So you take your mass there and you just kind of just slap it really quickly or just kind of, you know, hit it with a hammer. Okay. That's going to cause the entire system to respond. Okay. And typically the response that you're going to observe in these kind of dynamic systems is you're going to see some kind of oscillatory response. And so if we were to plot that out, and so if on the horizontal axis we have time, so we're plotting out kind of the response of our system as a function of time. Vertical axis, we have the position of the mass, x of t, okay? So an oscillatory response means that our position of the mass is going to oscillate kind of back and forth, okay? And so it's going to look something like this. So that's kind of what it means to oscillate. So, it kind of goes kind of back and forth, okay? And if you notice kind of the way that I drew this oscillation is kind of very intentional. And so if you notice that the amplitude of the peaks is kind of decaying as a function of time, okay? So that's very common as well. So nothing, unless you have kind of a perpetual motion device, most vibrations or most oscillations kind of die down with time, right? And so if we were to kind of plot this out, our x of t here will be a multiplied by e to the minus bt multiplied by sine of omega t, keep it sine omega t. Where if you kind of break down this response here, we have a times e to the minus bt. What we have here is called a decaying amplitude. So this shows that the amplitude of oscillation for this, for this response is decreasing as a function of time. Okay. Then we have sine omega t, and so sine omega t, that is the oscillatory component. So that's the part that's going to kind of oscillate kind of back and forth. Okay. So this is kind of the general response this is kind of the dynamic response for kind of any kind of structural system, okay? So if you imply an impulsive loading, it may not be on a time scale that you can kind of observe kind of, clearly with your eyes, but there is some kind of vibration there, right? So if I were to take this kind of projector thing, if I were just kind of hit it like that, right? You can kind of see, well, I can see because I'm right in front of it, but you guys might be able to see. Zoom people, you definitely can't see, right? But each time I hit it, there's a little bit of oscillation that goes on. So it kind of like goes up and down a little bit, before it kind of settles into its kind of final position. So this idea that, when you have impulse loading, you apply to a structure, the dynamic response is almost always going to be, oscillation of some kind, right? This is especially true. This is especially true if you have a linear isotropic material, linear isotropic stress strain response in the system. Which, if you kind of notice in this class, that's typically what we work with. So typically, we work with materials. We assume just a very simple kind of linear elasticity for our response. So we're going to be in this regime, right? And so when we run the dynamic simulation on Thursday, you're going to observe. So If you haven't kind of, I know some of you have kind of done this activity with me before, but on Thursday, we're going to be simulating a car crash. And so we're going to be taking a car's frame and just kind of crashing against a wall. You're going to see a little bit of oscillatory response. That's because, that's a function of, we are providing an impulse loading. And so the car is going to be impacted by the wall only for a very brief moment of time. But it's also response, or it's also as a result of kind of the linear elastic material that we're assuming for this car. Okay. Okay. And so kind of the character of the oscillatory response is kind of a big part of doing dynamic structural simulations. Any questions on this so far? Okay. All right. So the big question is, how do the properties of our structure or the properties of our, our simulation, how does it affect the dynamic response? And so in particular, just for the case of simplicity, we're going to focus on the properties of our mass spring damper and see how that affects our dynamic response. So we'll go one by one. So we'll start with the mass. Okay, so generally the mass represents the amount of inertia there is in your system. And so if you kind of remember the definition of inertia, inertia is the ability of a structure to resist changes in motion. Okay, so the more mass you have, the more inertia you have, the more you're going to resist changes in your. So generally what we say is that as the mass increases, and so if you increase the mass of your system, it's going to reduce the frequency of the dynamic response. Because the frequency of the dynamic response, that kind of represents, basically each time the mass kind of, oscillates up and down, that represents kind of a change in momentum. And so if you have more mass, it's going to resist that. And so the more mass you have, the smaller the frequency. Okay. Number two, let's look at the stiffness. So stiffness, if you kind of think back to what a spring constant represents, a spring constant tells you, how much restoring force the spring is going to apply, right? Because that's kind of the hallmark of a spring. If you deform a spring, if you stretch a spring or compress a spring, it's going to apply a restoring force to kind of bring it back to its equilibrium position. Okay, and so every structure has a stiffness. And like I mentioned, that's a function of its material properties, and that's a function of its geometry as well. Okay, so the more stiff an object is, and the main property that you use to measure this is the Young's modulus. So the stiffness of a structure kind of has the opposite effect of the mass. And so the more stiffness you have, the more internal forces, the higher stresses you're going to have internally when you deform your structure away from its equilibrium position. And so the more stiff a structure is, it actually increases the frequency of the dynamic response. So mass and stiffness kind of work kind of opposite to each other. Okay. Now, granted, some of these, sometimes mass and Young's modulus are correlated for a material. So generally, the more dense or the heavier materials also have a higher Young's modulus. So those effects kind of cancel out in a way. But there are materials that are very light but have high stiffness, but also materials that are very dense and very heavy but have low stiffness as well. So kind of something to keep in mind. Okay, so the last property that we have is the damping. Okay. So damping kind of represents how well your structure can suppress the dynamic response. So how quickly can it kind of go back down and go back to kind of a static situation. Now, damping, between the mass and the stiffness, damping is a lot more difficult to quantify. So it's not something you can just kind of look at a structure and just measure the damping. Usually it's a very complex thing in terms of how the different parts interact, kind of the coefficient of friction, things like that. But generally the higher your damping, the more easily kind of the response gets gets suppressed. And usually the way that people measure damping is you don't usually measure it beforehand. Usually you kind of do an experiment or you do a simulation and you kind of observe the response, and then from that you kind of get an idea of kind of how much damping there is in that system. So damping, very hard to quantify, but it is there. You do have to kind of account for it when you're thinking about your dynamic response. Okay, so like I mentioned, a real life situation is kind of a lot more complex than this, and so it's not just going to be a straightforward mass spring damper, but a lot of your intuition in terms of how you understand how the system works. That intuition can also be applied to more complex situations as well. Okay. Any questions on this? Okay. All right, so let's go ahead and move on, right? And so that's all I kind of wanted to say about dynamic response. Let's talk about numerical solutions to unsteady problems. So basically, how do we actually solve these kind of transient situations within the context of finite elements? Now, this is the part, we have about 45 minutes, about 40 minutes. So this is something that, like I mentioned, this goes way deeper than kind of what we're going to talk about today. And so the goal of this section here is not to, give you a thorough background on the theory behind this, but just to kind of give you some familiarity with the terminology that's used, what each particular parameter, what particular setting it's used, because dynamic problems, they use kind of a very different, framework than our static problems. So it's important to kind of know kind of what these are before you kind of jump really into it. Okay. All right. So the first thing to kind of understand is that, when you do a dynamic simulation or a time-dependent simulation, the cost of the simulation is much higher than that of a static simulation. And so this cost is because of two things. So the number, first of all, just the number of computations that you have to do is much higher. And so, what some of you are going to see on activity 5 is that, we're going to spend maybe about 30-40 minutes talking about the setup of the activity. And then you're going to hit go, and then you're going to sit there and you're going to wait for like 5 to 10 minutes for the simulation to complete. So, the amount of time it takes is much higher. And sometimes this gets pretty extreme. And so, if you have kind of a very complex mesh, sometimes you have to, a lot of times I would say, for most practical cases for an unsteady simulation, you do have to run those on a supercomputer. Otherwise, just, a desktop computer is just not going to have the power needed to run these types of simulations, right? That's one thing. The other way where the cost increases is in the amount of memory that it takes just to even store the results. Right, because if you think about it, if you're simulating a time-dependent situation, that means your results are also going to change with time. So your deformation is going to change with time, your stresses are going to change with time, your strains are going to change with time as well. The only way to really visualize that is if your results were a video instead of a static image. Right. And so if you think of a video, so if you think of an animation as nothing more than just several static images kind of played back to back very quickly, right? If you think of kind of a typical kind of resolution, maybe you have maybe 30 frames per second, right? So even just to simulate 1 second of dynamic response, you need to do 30 static simulations just for that 1 second. And so that kind of gives you a sense of kind of how expensive these are. So dynamic simulations, part of the reason we don't do too much of it in this class is because we just don't have the computational power. Because if you really want to give a good treatment for this, we need probably access to a cluster of some kind. Okay, so that's one thing. And so you want to be really careful. So when you do run dynamic simulations, you want to make sure kind of make double, triple sure that everything is set properly. Because if you don't set something up correctly, your mesh doesn't look great, your boundary conditions don't look great. You're gonna have to wait a while before you can change it. Okay, so it's something to kind of keep in mind. Okay, the other thing to kind of keep in mind with dynamic simulations is that time is now going to be a variable that you need to account for in your response. And in fact, if you look at the governing equations for these time-dependent situations, our governing equations are actually going to change because there's going to be an additional unsteady term or an additional derivative with respect to time that we have to discretize and solve as well, right? And so to solve the time domain or to solve the time portion, we actually have to use another full collection of different numerical techniques that are kind of separate, but also kind of work together with FEA at the same time. So usually the way I like to think about it is that FEA or finite elements is used to solve for the spatial variation of your solution. Okay. So we've kind of seen that. So we've used FEA to solve for the spatial changes in the deformation or spatial distribution in the stress field in our simulations. Okay. The time field is solved using a collection of techniques called time marching schemes. So time marching schemes, that's just the name of the numerical method that's used to solve for the changes in time for a finite element simulation. Okay. And time marching schemes, again, there's a lot to discuss there. Not this is not kind of the venue for that, but we will kind of go over the basics. Okay. So basically the idea with time marching schemes is that the reason we call them time marching is that you kind of solve for the solution one step at a time. It's kind of, time is kind of fundamentally different than space, right? Because the thing with FEA, so the way FEA kind of works is that you have your structure, it takes up a certain amount of volume in space, right? You apply your boundary conditions and you kind of solve for the static response in the entire structure all at once. Okay. Just because if I were to look at the static response of this table, right? And so that corner of the table doesn't really care what I'm doing to this side of the table, at least not directly. And so you kind of solve for the entire table at once. Okay. Time is a bit different because time is a causal entity. And so what that basically means that what happens in the next time step depends on what's happening at the current time step as well. So you can really only solve time dependent problems one step at a time, right? So you can't solve it 3 steps in the future or 10 minutes in the future because it really depends on what's happening in the present. Okay, so the idea is like this. And so if you were to solve for the solution at the next time step, okay, so we represent that with a u superscript n+1. Right, so this is going to be equal to a function of u of n. Okay, so u of n, this is the function at or the solution at the current time step. Okay. So you need to know what's happening now before what happens in the future. Okay. And this is going to be a function of all of our our system parameters. So it's mass, spring constant, damping, density, geometry, things like that. Okay. Okay. So just like the static response, so static response depends on the loading, boundary conditions, material properties, all that stuff. So all that stuff is still going to matter, of course. But the most important thing is that you can only solve the time response one step at a time. Okay. And each time you solve for the solution at the next time step, you can consider that as kind of the cost of one static simulation. So you're kind of literally kind of marching the solution forward, kind of one step at a time, right? So one thing that you're going to find out that you need to specify in an unsteady simulation is that you do need to specify something called the initial condition. Okay, so the initial condition is different from the boundary conditions. And so the initial condition basically tells you the state of the solution at the beginning of the simulation. So at time is equal to 0. Okay, so that's going to be one of the most important things that we specify on Thursday is, what is the initial condition? So how is our system going to start? Because that's kind of the starting point for our time marching scheme. So you can't march forward in time if you don't kind of take that first step. And so the initial condition, well, I should say the initial conditions is kind of more where your starting position is, and then you kind of march from. Okay, any questions on this so far? Okay, good. Okay, so with time marching schemes, there are a few additional parameters that you have to specify in order to kind of define the trajectory of the time response. Okay. So these will be additional parameters that you have to specify on top of the static simulation. So on top of the mesh, on top of the boundary condition. So initial condition is one of them, right? So that's one thing you have to specify. But there are other things you have to specify as well. Okay. Now ANSYS does automatically specify some of these for you if you don't specify them manually. So that's kind of important to note. So we aren't going to specify everything here on Thursday because we're going to let ANSYS kind of choose it for us. But there is at least one that you have to do in every dynamic simulation. Okay. Okay, so the first one. This is a very common parameter that you have to set for most dynamic codes. So this is one we're going to let ANSYS kind of select this one automatically for us. But this is actually a very important parameter for the dynamic response or dynamic simulation. Okay, and that's called the time step size. Okay. And so remember, like I mentioned that, for a time marching scheme, you're going to march the solution forward kind of one step at a time. Okay. Now the time step size tells you how much physical time there exists in between each of the different steps in your solution. Okay, so the time step size symbolically, usually we give it the symbol delta t, or sometimes we call it dt. Usually it's delta t if you're writing with a pencil and paper. If you're writing an email, it's usually dt because you don't want to pull out the symbol for delta. It depends on kind of the context, but they kind of mean the same thing. So visually, I like this kind of visual here, where if you think of your dynamic response as kind of a timeline, right? Right, so you're basically simulating the response of your structure, as time kind of goes on this line, right? But you're not solving for the system response at every single possible time here. You're solving it at discrete points in time, on the snot. Okay. So this may be n is equal to 1. This is n is equal to 2, n is equal to 3, n is equal to 4, 5, and 6. Okay. So these are all the discrete points in time in which you're solving for your response. The time step size is the amount of time that elapses in between each of these points that you're computing. So this distance here, that's delta t. Okay. Now, in the most kind of basic setup for an unsteady simulation, you typically specify a constant value for delta t, and so the space in between the time points is kept constant. Okay. This delta t, this is delta t, and so on and so forth. Okay. Most of the code that I've worked with kind of in the past, before ANSYS kind of uses this framework where you specify a constant time step size, and that time step size is kind of maintained throughout the entire simulation. Okay. Usually it makes kind of post-processing a little bit easier, and it makes it a little bit easier to kind of interpret your results. But it can sometimes lead to a little bit of waste of space. So sometimes what the software can do, and this is what ANSYS does, is that it dynamically chooses the time step size as you go along the simulation. Now, what are some theories, or how do you select a time step size? So the time step size, you can think of it, your intuition for the time step size, should be very similar to how you think of the mesh size. And so generally, the smaller your time step size, the more accurate your simulation is going to be. Okay. But just like the mesh size, as we know, kind of the smaller that you set your mesh size, it's going to make your results more accurate, but it's also going to increase the cost as well. Same thing here. So a smaller delta t, it's going to increase your cost, which sometimes is actually pretty significant for a dynamic simulation as well. Okay, so the idea with kind of dynamically adjusting the time step size is kind of the same theory of why you would refine your mesh, right? So we spent a lot of time in this class talking about you should refine your mesh in the areas where you need it in the simulation, right? And so in areas in your model that have a high stress concentration, that maybe have high solution gradients, those are areas where you want to refine your mesh so that you kind of spread your cost out kind of a bit more efficient. Okay. So the same thing with the dynamic response. And so with the dynamic response, oftentimes your dynamic response is not even in terms of the changes. So there might be a lot of sudden changes at a very small period of time, and then maybe you have a long period of time where not much has happened. And so the idea with adjusting the time step size is you can make your time step size really small for those times where a lot of activity is happening, and then when not much activity is happening, you can kind of spread it out a bit more. But like I said, it does get a little bit complicated, with the post-processing, when you do have an adjusting time step size, unless you have a software like ANSYS that kind of organizes it all for you. Sometimes it can be very hard to kind of process everything. So for most softwares that I've seen that I've worked with personally, we kept kind of a constant time step size. But there are motivations, there are reasons for why you want to adjust it in real time. Right? Okay. So how small should you set your time step size? That's kind of the million-dollar question. Okay. So the general rule of thumb that I use is think about kind of your dynamic response and think about how quickly things are changing, in your dynamic response. And just remember that, whatever you set for the time step size, that's going to be the resolution of, whatever you can capture in your simulation. Okay. So I was going to say, think about. Think about how quickly things change in the dynamic response, right? And so if you expect things to change, on the order of milliseconds, right? And so, the solution 1 millisecond is going to be different from the solution in the next millisecond. And you want to make sure your time step size is small enough to capture that change. Okay. So generally my rule of thumb is, if you can think of a time scale in terms of how things are changing in your simulation, at the very least, your time step size should be 1/10. So for example, a lot of the work that I kind of do for my own research is I do simulation on cardiovascular flows. And so, a very natural time scale in cardiovascular flows is the rhythm of the heart. Okay. So typically for a normal person, their heart beats about once per second. So that's about 60 beats per minute. Okay. And so, that means that our time step size, if things are going to be changing on the order of 1 second, maybe you want to set your time step size to maybe be about, 0.1 seconds at the very least. Okay. Oftentimes, I want to set a time step size that's a lot more fine than that because there are certain flow characteristics that are happening on a much smaller time scale. But at the very least, I should set something, I know things are going to be changing on the order of 1 second. And so at the very least, I should set it to be 0.1 seconds. Okay. So think about, your dynamic system, how quickly things are going to change, and then set your time step size to be at least 1/10 of that. Maybe sometimes even more fine than that as well. But 1/10, I would say, is the bare minimum in terms of, being able to capture that accurately. Okay. Any questions on this? Okay. All right. So we spent a lot of time talking about the time step size, even though it's not something we're going to set on Thursday because, in most other softwares, time step size is probably the most important parameter you set for the time marching scheme. Okay. Now, the other parameter that you have to set, besides the time step size, and this one you will have to set on Thursday, is the end time for your simulation. Sometimes in certain softwares, you'll specify this just by the number of time steps that you want to simulate. So this parameter here is pretty straightforward. So this just tells you, how much time do you want your unsteady simulation to simulate, before it quits. And so again, for this parameter here, you want to think about how long it's going to take for your entire dynamic response to resolve. Okay. And make sure you set your end time so that you capture all of that kind of dynamic response. And so for instance, on Thursday, we are going to be simulating a car crash. A car crash happens very, very quickly. And so, most of the action actually occurs over the course of a few milliseconds. And so what you're going to see is that, our end time, is going to be actually very short because, most of what we're going to simulate is going to be happening in just that small time frame. Okay. But, if you're simulating something like a heartbeat, you want to make sure you capture the entire heartbeat, make sure your end time is something in the order of 1 second or 2 seconds, something. All right, any questions on this? Okay, all right, so that was kind of the 30-minute, less than 30-minute overview of time marching schemes, but again, I am kind of glossing over a lot of details. All right, so last thing that I want to go over in class today are the two main kind of tools that ANSYS has for transient simulations, and kind of what are the differences in between the two, because sometimes people get them confused. Let's talk about explicit dynamics versus transient structural. So on the surface, these two tools kind of do more or less the same thing. So you have kind of a structural system, a dynamic response you want to simulate, and both of these will allow you to do that. So actually, for the activity on Thursday, so on Thursday, we're going to use explicit dynamics. You could probably do it in transient structural as well. So you should actually get probably the same thing, more or less. The difference between these two techniques is the technique in which they apply the time marching scheme. So time marching scheme, there's not just one time marching scheme. So in fact, there's kind of a family, or I should say several families of different time marching schemes that work. And so, there's kind of two big kind of families or two kind of big categories of time marching schemes. So there are explicit schemes and there are implicit schemes. So explicit dynamics obviously is an explicit scheme. And then transient structural is kind of the default implicit scheme within ANSYS. Okay, so what do these terms mean? So what does it mean for a time marching scheme to be explicit? And what does it mean for a time marching scheme to be implicit? Okay. So I like to think of kind of the analogy with kind of data extrapolation. So explicit time marching is very much like extrapolation of data, Whereas implicit time marching is more closely approximating interpolation of data. Okay. And so with explicit time marching, we are basically only using the information in our current time, to estimate what the solution is going to look like in the next time. And so we're kind of, some people think of it as kind of like shooting in the dark because, you're only looking at the present and you're kind of, trying to guess what's going to happen in the next time frame. You're making a very educated guess. It's not a random guess, but, it's, in a lot of ways, it's kind of unstable because, you're kind of not using a lot of kind of stability, a lot of kind of tricks within the numerical code to get you stability. And so kind of the analogy that I'd like to use that if you have some data, so let's say that, your data is kind of following a certain trend like this, okay? So all the things in pink here, these are all the known data. Right, so with explicit time marching, you're kind of making a guess of what the next data point is, without really kind of any kind of safeties. And so you're kind of just looking at your current position, the current trends, and you make a guess based on that. Okay. And so your next point, okay, this right here is what's called an extrapolated data point. So it's just based purely on kind of what's happened in the past, and then you kind of make a guess what's happening in the next step. Okay. So with explicit time marching, what you guys have to worry about as kind of a person that's using the software, generally explicit time marching is a bit more unstable. And so you're much more likely to get a solution that makes no sense at all. Okay. But it is a lot faster than implicit time marching. So that's part of the reason we're using it on Thursdays, because it is much faster than if you were to try to run the job on transient structural. I think a couple of years ago, I had a student that did try to run this activity using transient structural, and I think his computer just kind of crashed. And so I wouldn't recommend it unless you have a lot of confidence in your computer. But with explicit, the cost is generally a lot lower. Okay. The main thing to worry about with explicit time marching is that because the solution can be more unstable, there's much stricter requirements on the time steps. Okay. And so the way these kind of methods work is that the stability and the accuracy of these simulations depends very strongly on the time step size. And so there's a very strict requirements. And so you need to kind of set that time step size to be low enough so that you get a stable solution. Okay. So generally, my rule of thumb is that if you have a phenomenon that's going to be occurring very, very quickly anyway, and so just for the sake of accuracy and just for the sake of capturing your phenomenon, you're going to set a low time step size anyway. You might as well use an explicit scheme because it's going to be much faster. And that's exactly the case of what we're gonna do on Thursday. So we have to set a small time step size anyway, because a car crash happens so quickly. So we might as well use an explicit scheme because it's gonna be much faster for us anyway. Okay. And in fact, most codes that I've worked with do use an explicit scheme, although they do some extra tricks kind of to increase the stability. But explicit is very common just because it is much easier to implement in most cases. Okay. So that's what we're going to do on Thursday. Any questions on explicit time marching? Okay, so very quickly, the other option that we have in ANSYS is transient structure, which is an implicit scheme. Okay. So with implicit time marching, there are some additional checks that the software has to do just to make sure the solution kind of makes sense. And so, whereas explicit time marching, like we kind of just say it's just a guess. Implicit time marching, you can kind of think of it as like guess and check. Okay. That's kind of the best way that I can kind of describe it without, diving too much into kind of the details of the algorithm. Okay. Now, this additional checking is not just a trivial thing. So this does actually increase the cost quite significantly, just because it drastically kind of changes the nature of the computations that must be done to get this. Okay. So instead of just simply think of it as, instead of doing a matrix multiplication, you're instead doing a matrix inversion. So you have to invert a matrix, which is a lot more time consuming and a lot more difficult. So that's kind of the main thing is that, if you use an implicit scheme, your cost is going to go up significantly. Okay. But the trade-off is that, because you're doing a lot more computations, your solution is almost guaranteed to be stable. And kind of the byproduct of that stability is that, you are much more free to choose a much larger time step. So those restrictions on the time step size are much, much less. And so you can set it to be kind of almost whatever you want. So usually in the most of the cases where you're going to see an implicit time scheme, are cases where you want to simulate something that occurs over a very long period of time. And so a lot of times, you're gonna have a dynamic response, but it's not gonna happen over the course of, 1 second or 2 seconds. Maybe you want to simulate something that occurs over the course of 30 minutes or an hour. And so if you do that with an explicit scheme, you're gonna be chugging out calculations for forever. And so with an implicit scheme, you're more free to choose a larger time step size and still get a stable solution. So there are applications for this, and I will say that it is quite rare to have a software that does an implicit scheme, because most of the time implicit schemes is something that you learn in the classroom. But when you get to actually apply that to kind of more practical problems, it becomes much more difficult to apply. So the fact that ANSYS actually has this is actually a pretty big deal. Not every software will have this capability. But with that said, because not that many softwares have it, most people don't think of their dynamic problems in the sense where you can actually take advantage of this. So for the most part, most people are going to be using the explicit time scheme, explicit dynamics, but there are applications for implicit schemes as well. It's just that they're a lot more rare in the space of kind of finite elements and stuff. All right, any questions on this before we wrap it up for today? Yes.
So in ANSYS, can we just switch from implicit to explicit, or?
It's not that easy, because explicit dynamics and transient structure are kind of two separate systems. You're gonna have to close the project and kind of start a new one in transient structure. You do all the same settings, but the way they set it up, where it's not so easy to kind of switch. All right, any other questions? Okay, all right, so that's all we got time for today. And so when we come back on Thursday, we'll do activity 5, and then we'll go on spring break. So thank you guys for coming today. Hope you guys have a good rest of your day, and I will see you guys on Thursday.
Yeah.
I mean, the requirements are only one, but you're of course open to kind of add or try out different material, as many as you want.
The arm on the factor that into the fixed board back there.
It depends on your loading, so it depends on kind of what situation that, because I've seen people, they've done situations where that arm very important, if it's supporting the weight of the entire thing. I've seen other ones where people just suppress it, and then they just have things sitting on the ground. Exactly. Yeah, in fact, I would recommend it. So it depends on how you're loading it.
Okay, that makes sense. So working on the.
Okay, yeah, let's meet, well, next week, spring break, so we can meet afterwards.
I'll finish it when I send it. I'll send it to you when I finish it.
Okay, sounds good. Hey, man, how's it going? Good?
I was actually news.
Okay,
Mistake.
okay.
The values in general.
Yeah,
It seemed excessive side.
okay,
So. Further. Deeper dive just into my setup.
yeah,
I noticed that I made a very big mistake.
okay,
So where I was using fluid, the
Yeah.
assigned material was aluminum.
oh,
Yes.
oh, for the walls?
Yeah.
Oh, okay,
So when I
okay.
redid it.
yeah,
The values made a little bit more sense.
oh, for like the pressure?
Yes.
Oh, okay,
In
okay,
terms of pressure drop and all that.
oh, okay, that's great, that's great,
The magnitude is, it's relatively the same, but the magnitude is much lower.
okay,
And I redesigned, I made another version.
yeah,
Yeah.
Decrease that bend,
okay,
so it was more smoother, and then I
Yeah.
got a pressure drop of 460.
460 Pascal.
Yes.
Oh, that's great, that's much better than 450
what-
Pascal.
Yeah, one of the things that I have is it still has that same pressure. It also increases the quality.
Yeah.
Yeah.
So I could just.
1.75.
Yeah.
I did it Okay. Stress is like.
No, that is older as well.
Yeah.
Stress is still concentrated on.
Yeah, I mean, that's,
On that
it's probably hard, it's probably hard.
Maybe
to
it's
probably
the
avoid that. I think probably just trying to lower that overall magnitude from that. Yeah, yeah, I think just the way that the device is structured, I think you're always gonna have stress concentrated there, we have a stagnation point there anyway.
Yeah.
So I think that's always gonna be hard, it's just getting that value to the lowest. That's gonna be, but yeah, that's much better.
I'll try to
Yeah.
play with it a little bit more. I'm trying to hopefully, I'll just do all this increase the like
Okay,
within the design itself, because those bends within the device,
Yeah.
those showing a little yellow.
okay,
So like it is an area. So
okay,
I'll try to play with it a little.
okay, sounds,
And I also wanted to ask you about like.
Yeah.
I know Monday is a spring break.
we can still meet on Monday if
Okay,
you want.
yeah.
Yeah, cause I know you're defending soon, so,
Yeah.
yeah, let's meet on Monday, 1 o'clock. Okay, yep.
Question to mention.
Yeah.
The product template says these like keywords, just wondering like.
Oh, yeah, don't worry about that. I keep forgetting to take that out of the template. But the keywords so that template is actually used, it's actually a template for like a scientific article. And so typically those keywords are like your Google search words. Yeah, but you don't need them for the report. You can just take it.
That makes sense. I was confused.
Hey, how's it going?
Good, yourself?
Good.
What class is this?
This is graduate finite elements, EGME 540.
That's cool.